Are you ready to enter a hidden world where fractions of a millimeter can mean the difference between flawless performance and catastrophic failure? This is a world where glowing metal transforms from raw coils into instruments of deadly precision, and where every detail is dictated by physics, chemistry, and engineering mastery. Over 12 billion rounds of ammunition are produced every single year, destined for soldiers, law enforcement, hunters, and sports shooters. Each one is not just a piece of metal, but the result of an intricate process where pressure, heat, and geometry are measured to impossible accuracy. In this journey, you'll see the full story from choosing the right alloy and gunpowder to advanced tests where muzzle velocities approach 300,000 feet per second. This isn't just about bullets. This is about how science, technology, and human ingenuity push manufacturing to the very limits of possibility. Factories around the world produce hundreds of millions of rounds annually, each subjected to inspections measured in microns. The story begins with brass, 70% copper, 30% zinc. Gigantic coils arrive, weighing up to 6,000 pounds, carefully packaged to prevent oxidation. These rolls are flattened at blistering 600 degrees Fahrenheit to make the metal pliable. Even the slightest imperfection means rejection. Then precision stamping machines, operating at lightning speeds up to 250 strokes per minute, punch out perfect discs called blanks, each about 3/4 of an inch in diameter. Heated again to 800 degrees Fahrenheit, these blanks are drawn under massive 100-ton hydraulic presses, stretching and thinning them into casings. Step by step, they begin to take shape, but there's danger in haste. Casings are annealed at 1000 degrees Fahrenheit to release stress and prevent cracking during use. They're cooled, cleaned in acid, and sent through lasers and sensors that check weight, thickness, and even sound response. A microcrack invisible to the human eye triggers instant rejection. Only those that pass continue to trimming, primer grooves, and mouth expansion. Then comes the primer, a miniature explosive at the heart of every shot. Whether lead-based or lead-free, primers are tested for perfect sensitivity. Too reactive and they're dangerous, too weak and they fail. Machines install each primer with micrometer accuracy, locking them into place to withstand recoil. Next, gunpowder. A pistol round may carry 5-7 grains, while a rifle round holds about 24 grains. Automated systems weigh down to 1/1000th of a grain. A tenth of a grain's error could destroy both shooter and weapon. The bullet itself is pressed into place with immense force, the casing mouth crimped tight. Advanced cameras with AI check each round in less than a second. At massive plants, the rejection rate is below 0.3%. Then packaging. Civilian rounds are boxed in plastic trays and shrink wrap, while military rounds are sealed in steel containers, airtight with anti-corrosion lining, marked with caliber, batch, and QR codes. One box can hold over 1,200 bullets, weighing 40 pounds. In high-demand times, wars, crises, elections, factories run 24/7. A single packaging line can produce up to 300,000 bullets per shift. Inside these plants, safety is everything. Floors are anti-static, humidity is tightly controlled, and air filtration removes toxic dust. Workers wear flame retardant or anti-static suits, with all jewelry and electronics banned. Robots handle the most dangerous work, measuring explosive mixtures, sealing primers, and loading powders. Fire extinguishers, sprinklers, and blast containment chambers stand ready. Training is constant, because mistakes can be fatal. In 1998, a U.S. gunpowder plant exploded after storing incompatible chemicals too close together. The blast equaled several tons of TNT, killing workers. That disaster still stands as a grim reminder that safety matters more than speed. Now picture another colossus of modern industry, the press brake. Imagine a machine longer than a double-decker bus, applying millions of pounds of force, bending thick steel as easily as you fold paper. These machines form everything from Tesla car bodies to armored military vehicles. A 10-foot-long steel sheet nearly half an inch thick requires at least 350,000 pounds of force to bend. Modern CNC-controlled press brakes achieve accuracy down to 4/10,000ths of an inch. Their punch descends at 4 inches per second, slowing to fractions for perfect control. Automotive giants, Ford, GM, Tesla, rely on them for frames and panels. In aerospace, tolerances are so extreme that even 2/1000ths of an inch of error could ruin aerodynamics. At Oshkosh Defense, press brakes exert 2 million pounds of force, bending steel over an inch thick into armored plates. Shipbuilding uses presses several stories tall, not just bending but stretching and twisting metal into hulls capable of withstanding storms. Errors here mean disaster at sea. And where there are presses, there are guillotine shears. Once tools of execution in 18th century France, today their industrial descendants cut metal sheets cleanly and silently with surgical precision. CNC controls set length, angle, and speed, while safety systems guard workers. They can slice through steel inches thick, preparing it for further shaping. From air ducts to furniture to refrigerator housings, guillotines and press brakes keep modern life running. The largest hydraulic press in the world, built in the US during the Cold War, still works today, forming massive aircraft parts, nuclear reactor components, and even sections of rockets. And finally, what about the machines we cast aside? Every year, millions of laptops are discarded, yet they are far from worthless. Inside each lies a hidden trove: gold, silver, copper, and dangerous toxins like lead and mercury. Specialized recycling centers handle them with astronaut-like care. Workers wear protective suits to shield from sharp edges, toxic dust, and even the risk of residual electric charge from capacitors. Lithium-ion batteries are removed by hand and stored in sand-filled containers because a single puncture can cause an explosion. Hard drives are pulled out and destroyed, sometimes shredded, sometimes melted, ensuring no sensitive data survives. Before anything else, batteries and hard drives are removed. Why? Because lithium batteries can catch fire, and hard drives may still hold sensitive data. Once those risks are gone, the laptops are ready for dismantling. The first step is brutal but precise. Each laptop rolls onto a conveyor belt where a massive hydraulic press, exerting up to 5 tons of force, slams down. With a sharp crack, the casing splits apart, making internal components accessible. From there, the process becomes surgical. Robotic arms equipped with screwdrivers, spinning at 5,000 revolutions per minute, quickly strip out keyboards, speakers, and cooling systems. Pneumatic grippers clamp onto screens, while high-precision blades glide along their edges, snapping displays free with a barely audible crack. In under 2 minutes, a complete laptop is reduced to individual parts, but disassembly is only the beginning. Next comes sorting. Robots and humans work together here. Plastics are scanned to determine their type, some destined for reuse, others converted into fuel. Metals are separated using magnets and induction detectors. Ferromagnetic materials, like steel, are pulled aside with powerful magnets, while copper and aluminum are sorted electronically. Glass from displays is shredded, purified, and repurposed for new screens or even construction materials. The motherboards and chips go through an even more fascinating journey. First, they're inspected. If they still work, they may find new life in the secondary market. If not, they're melted down in high-temperature furnaces, burning away organics and leaving behind pure metals: gold, silver, copper, and palladium, ready to re-enter manufacturing. Hazardous elements, like mercury, cadmium, and lead, are carefully extracted under sealed conditions. Mercury from old screens can be reused in medical instruments, while lithium from batteries is harvested for new power cells. Everything has its place. Plastics are compacted into bales, metals are pressed into dense cubes, glass is crushed into granules. Even lithium batteries are sealed in non-flammable containers, often cushioned with sand to prevent ignition. Each material is then transported, by truck, train, or ship, to specialized plants around the world. Metals head to smelters. Plastics go to polymer recycling centers. Glass is turned into insulation or new displays. Circuit boards are dissolved in chemical baths to extract their rare and precious metals. Even hazardous waste is neutralized under tightly controlled conditions. The process may take hours, days, or even months, but the outcome is extraordinary. A laptop that once powered your work or entertainment is reborn as part of a car engine, a skyscraper frame, a new smartphone, or even another laptop. Nothing truly disappears. It transforms. But while old laptops are broken down, across the world another kind of assembly is taking place. Not destruction, but creation, on a scale almost impossible to comprehend. In Toulouse, France, lies one of the largest aircraft manufacturing plants on Earth, the Airbus facility. Spanning over 11 million square feet, this is where giants of the sky are born. The legendary double-decker A380, the fuel-efficient A350, and other Airbus aircraft all take shape here. Unlike laptops, which are dismantled piece by piece, these flying marvels are assembled from millions of parts shipped in from every corner of the globe. The wings come from Britain, the fuselage from Germany, the tail from Spain, engines arrive from the United States. Even Canada and China contribute critical components. These colossal pieces are transported by ship, truck, or even the custom-built Beluga cargo plane, designed specifically to carry oversized aircraft sections. Inside the assembly halls, the process is nothing short of astonishing. Giant cranes lower massive fuselage sections into place. Robotic systems align them with microscopic precision. The wings, each weighing tens of tons, are attached to the body with extreme care, as this joint determines the aircraft's aerodynamic stability. Miles of cables, pipes, and hydraulic lines are threaded through the narrow spaces inside. Avionics systems, essentially the aircraft's brain, are installed in sterile environments to prevent contamination. Then come the engines, lifted into place by hydraulic cranes. Each engine must be perfectly aligned, as even the slightest miscalculation could endanger flight safety. After the structure is complete, the aircraft undergoes grueling tests. Brakes, hydraulics, avionics, all are pushed to their limits on vast test grounds, covering 2 million square feet. Finally, the aircraft enters the finishing phase. Before it can wear the colors of an airline, it must be painted, an intricate process that requires up to 3,300 pounds of specialized paint. First, the surface is treated with anti-corrosion coating, then layer upon layer of polyurethane paint is applied, ensuring durability against UV rays and harsh weather. Logos and liveries are added, sometimes requiring weeks of meticulous work. The cockpit, however, is where the real magic happens. Built separately, it houses up to 5,000 individual components, controls, sensors, displays, and navigation systems. Once fully assembled, it is integrated into the aircraft with surgical precision. Any error here could mean disaster in the skies. It takes over 10,000 specialists, engineers, technicians, testers, to bring a single aircraft to life. The cost? Around $445 million for an Airbus A380, yet the result is breathtaking. A machine weighing hundreds of tons that can soar gracefully across oceans, connecting people and cultures across the globe. And so, on one side of the world, machines are taken apart. On the other, machines of unimaginable complexity are built. Both processes are driven by the same principle, transformation. Old laptops may turn into the metals used in new aircraft, while those aircraft, decades from now, will themselves be dismantled and recycled into the technology of the future. The cycle never stops. What we throw away today may be reborn as tomorrow's innovation, and what we build today may one day be taken apart, its materials flowing back into the endless loop of creation, destruction, and rebirth.